Okay, so today we're going to do about resultant forces and Newton's first law. But before we can talk about those, we need to just do a quick recap on the difference between scalar and vector. So something that is a scalar quantity has a size. You could say it's got a magnitude. Magnitude is just a fancy way for saying size. So if something is scalar, it has a size or a magnitude. They mean the same thing. If something's a vector, it's got a size or magnitude. They mean the same thing. It's got a size and a direction. So if you talk about mass, how much stuff, how much matter something is made of, that doesn't have a direction, but it does have a size. So mass is something that is scalar. Vector, mass is not a vector because mass doesn't have a direction. So where am I going with that? Well, if we were considering, so I've got a car, the car is travelling along, and we're going to say that it's travelling with a speed of 20 kilometres an hour. I'll put that down in the corner. So the car has a speed of 20 kilometres an hour. It's going around the roundabout. It's going around the roundabout. It's staying at 20 kilometres an hour. So the speed isn't changing because it's always travelling at 20 kilometres an hour. But the velocity is constantly changing. And to answer that question, or to explain why, you need to know that velocity is a vector, speed is scalar. What did that mean? So scalar, it's got a size, no direction, just a size. Vector, it's got a size and a direction. So because speed is scalar, speed doesn't care about which direction it's travelling. When it's going downwards here, down towards the bottom of your screen, the speed is 20 kilometres an hour. When it's going upwards, the speed is 20 kilometres an hour. Because velocity is a vector and it does have a direction, well, when it's moving upwards here towards the top of the screen, that is the opposite direction to that. So when a car is going round a roundabout, even if the speed is staying at 20 kilometres an hour, the velocity is constantly changing because velocity is a vector, which means it has a direction. So as long as the car is constantly changing which direction it's going in, it means the velocity is constantly changing. Okay, so that's a quick recap. What we're actually going to be talking about today for resultant forces and Newton's first law. So if we're going to talk about forces, we can't talk about resultant forces until we talk about forces. Forces are vectors. Forces have a size and they have a direction. The unit of force is the Newton, which we write with a capital N. So if we're talking about forces, forces are a vector, so they have a size and a direction. So we draw forces with an arrow. So if I just draw a few forces here. Okay, arrows are really useful for showing forces because they give it a direction. Obviously, this one's going to the left, these two are going to the right. So the arrows for the forces show the direction, and the length of the arrow shows the size. So this one might be 100 newtons, that one might be 70 newtons, and that one might be 20 newtons. So the longer the arrow, bigger the force. And then when we talk about resultant forces, so a resultant force is just where you've simplified forces, and you do that by adding together forces if they're in the same direction or subtracting forces if they're in the opposite direction. So as an example, I've got a train. So if we're going to draw the forces on the train, so we're going to have the weight of the train going downwards. So let's say that is 1,000 newtons. We've got the force on the ground pushing the train up. So we'll say that is 1,000 newtons. We've got the thrust from the engine pushing the train forwards. Make that a bit smaller. So we'll say that is 500 newtons. And then we've got the drag or the air resistance pulling the train back. And we'll say that is 200 newtons. So those are the four forces on the train. So we've got 4 separate forces at the moment, and we want to simplify them to work out the resultant force. So how do we do that? Well, we add together forces if they're in the same direction. And in this example, we don't have any forces that are in the same direction. So we do the second one, we subtract the forces that are in opposite directions. So if we look at our picture, we've got 1,000 down and 1,000 up. So 1,000 minus 1,000 equals 0. So we can cancel those out completely. And we've got 500 to the right and 200 to the left. So 500 minus 200 is the same as 300 newtons. So if we want to simplify them all down, we can cancel that one, and we just end up with 300 newtons that way. And what we would say is 300 newtons in this example is the resultant force. So if we had a helicopter, so we've got a helicopter and we'll say the weight is 200 newtons, the lift is 300 newtons, and we'll just leave it at that. We'll just make it a nice easy example. How can we simplify that? Well, they're in opposite directions, so we need to subtract them. So we have 300 minus 200, so we can cancel them all out, and 300 minus 200 leaves us with 100 newtons that way. And that's how you can work out resultant force. Just do one final example. Let's say we have the sea, got a boat, and we'll go with stick an engine on the back of the boat. Beautiful artistic talents here with a propeller. Right, so forces on this one, we're going to have weight of the boat, well, let's call it 500 newtons. We're going to have the force from the water pushing the boat up, 500 newtons. We're going to have the engine pushing the boat forward with 200 newtons. There's going to be drag backwards, so the boat's trying to push forward in the water's pushing the boat backwards, and we're going to say that that is 100 newtons. But we're also going to say that there's a current on the water here, and the current, so the tide is taking the water that way, and so we'll have a force of the tide of 100 newtons. So when we want to cancel all these out, these are opposite directions, so 500 minus 500 equals 0, so we can cancel those out. These, if you remember, if they're in the same direction, we add them together. So 100 plus 200 equals 300 newtons. So we've simplified those two forces and had 300 newtons. And now these were in opposite directions, so we've got 300 minus 100. And so we end up with a resultant force of 200 newtons going that way. Now you should be able to quite easily work out in any question how to work out the resultant force. We'll talk about balanced and unbalanced forces. If the forces are balanced, it means all the forces in all the different directions have cancelled out, and so the resultant force is 0. So if there is no resultant force, it means the forces are balanced. If there is a resultant force, like in this example, it means the forces are unbalanced. So if I get my car, I'll just do an example to show balanced forces. Let's say weight of the car, 100 newtons down, force from the road pushing the car back up, 100 newtons up. The engine's moving it, 200 newtons that way, and then the friction and drag is 200 newtons that way. They all cancel out, so 100 minus 100 equals 0, so that direction cancels. 200 minus 200 is 0, so that direction's cancel. So you would say that was an example where the forces were balanced, because the resultant force equals 0. And if there's no resultant force, it means the forces are balanced. So to do a different example, different car. So let's do this again. Let's say 200 newtons down, 200 newtons up, 1000 newtons from the engine, and only 100 newtons of drag. So 200 minus 200, they cancel. 1000 minus 100, well, that cancels down to 900 this way, so 900 newtons. So there is a resultant force, and if there is a resultant force, it means the forces are unbalanced. Okay, so the final part of today's lesson, move the plant stuff out of the way, is Newton's first law. So Newton's first law. So Sir Isaac Newton, the guy who, same dude who got smashed on the head with an apple and came up with a theory of gravity. This dude, or you might recognise him better from a picture when he's slightly older. So same guy as the gravity guy. He came up with 3 laws of motion. Today's video we're just talking about the first one. And the first one can be split into 2 parts. So Newton's first law, a moving object will continue to move at the same speed and direction unless an external force acts on it. And a stationary object will remain at rest, and rest means it's stationary. So it's basically a stationary object will remain stationary unless an external force acts on it. And you can use the bit we've just done about resultant forces to work out what will happen to objects. So just go back and do a couple of examples for this one. So we've got our train, and we'll go for 1000 newtons down for its weight, 1000 newtons up from the ground pushing upwards on it, and we'll say the engine is putting out 1000 newtons that way, and we'll go with the air resistance is 200 newtons that way. So what's actually happening to our train? So first of all, we need to work out if there's a resultant force or not. So 1000 and 1000 cancel out. 1000 that way, 200 that way. So we subtract them and we end up with a resultant force of 800 newtons. And this is where we look at Newton's laws. So a moving object will continue to move at the same speed and direction unless an external force acts on it. Well, this does have an external force acting on it. So it's not going to stay at the same speed and direction because it's got a force on it. So what's going to happen to the train? In this example, the train is going to speed up. Or if the train was stationary at the start, is it going to stay stationary? So a stationary object will remain at rest unless an external force acts on it. Well, there is an external force. So if the train was moving, it's going to speed up. If the train was staying still, it's going to start to move. If we did a different example, so Jeff's in his car, he's driving down the motorway. Let's say he's driving at 70 miles per hour. His force, the car's putting out 900 newtons from the engine. The air resistance is 900 newtons. We'll say 100 newtons down, 100 newtons up. So let's work out the resultant force. Well, 100 and 100 cancel out. 900 and 900 cancel out. So there is no resultant force. So we go back to Newton's first law. A moving object will continue to move at the same speed and direction unless an external force acts on it. There is no external force because they've all cancelled. So the car stays at exactly 70 miles per hour because the force from the engine is exactly balanced out by the force from the air resistance going backwards. So one final example. If you had a car here, if I told you, so you can use this to work out other bits of information. If I told you that the car was stationary, so it's not moving, if I asked what is the resultant force, you can now work out that the resultant force must be 0 because it's stationary and it's going to remain stationary unless there's an external force on it. If I told you that the car was speeding up. So if I gave you 3 of these things, let's say I'm going to give you 100 newtons down, 100 newtons up. I'm going to say that there's 200 newtons that way. I'm not going to tell you that one. But if I said the car was speeding up, it's accelerating, it's getting faster, and I want you to tell me, you can't tell me the exact number, but you can tell me something about that. You can tell me that the question mark, whatever force that is, it must be less than 200. Because, going back to Newton's law, it's not continuing at the same speed, so there must be a force on it. And the force has got to be less than 200, so it can be speeding up. If the force was exactly 200, it would be staying at the same speed. If the force was more than 200, it would be slowing down. So let's change the question ever so slightly. If I said the car's doing that and the car is slowing down, it's getting slower, tell me about this number. Well, this must be bigger than 200. So if I said it was 201, then that cancels, 200 minus 201 leaves us with 1 Newton that way. So it would be ever so slightly getting slower. Now in the question, you didn't know it was 201, but you know it was at least 201. It might have been 300, which would have given us 100 that way. It might have been 20,000, so we're getting slower much, much quicker. But using Newton's law and the resultant forces, so if the forces are balanced and there's no resultant forces at all, if an object's staying still, it stays staying still. If an object's moving, it carries on moving at the same speed. So if there's no resultant force, the speed stays the same. If the speed is changing, it means there must be a force on it. Hopefully, that's given you enough information that you can go away and answer some questions on this.